Hello everyone, we're back and we're going to look here, or we're in the middle of something, but we're going to look off to the side here and how you actually go about sliding vectors using triangles. I'm off, the white's off to the right side, and so I'm going to talk about this concept of a free body diagram right there with a couple, three forces on it. And so I'm going to put the most obvious one down, and we're going to realize that forces have magnitudes and direction. I'm going to give these all the same color. We'll call that typically a weight. And this might be something like a direction here and a direction there. And we want to make sure that we've got knowledge of how we put things that are the same vector quantities in the same color. So when these are all brown, we know they're all forces. And so very typically, either by convention or otherwise, you might label that up and have it with some values or some scale. Though all reality is very often you're trying to think this out and you're not necessarily always pulling a scale. So in this case, we can think of that as 10, the sense that this would be, your thumb is about 1 inch wide, this would be 10, 20, 30, 40, 50, and these others would then lay on top. How do you go about adding vectors? You're going to see later on there's going to be this kind of shifting and sliding of vectors, but you have to add them from their point of concurrency. Every vector has a magnitude and a direction in 2 dimensions or 3 dimensions, and you generally want to slide your vectors up and down that line of force, that's called, so that they are emanating or they have their tails coming from the point of concurrency. So you have here 3 force vectors, and then this is how you go about adding them. You decide you're going to start with a 1. You might number them, call those 1, 2, and 3. Go into some logical direction, and what you do is you kind of walk down the vector from here to here, and then realize you now have to slide that second vector, so you add them tip to tail and tail to tip. We'll see there's lots of ways to do that in CAD with an offset or a copy parallel. On your sheet of paper, it becomes easiest if you do this. You learn to slide things like this. So you learn to kind of lay this out, if you would, so the hypotenuse are together and slide it along. And you got to be very careful as you're doing this that you hold it down quite tough. You're not going to get exact solutions here, but you'll be able to get probably more exact than some of you might get out of a calculator, because you'll tend to have errors in signs when you do a calculator. So you just draw that distance out along here. You hopefully have access to a set of dividers, or a scale, and so right now you're going to go ahead and use that divider here. That was 1. Now you're going to want to transfer, you already transferred the direction, so you can go here with a set of dividers. You can go here and say, this now is my second vector. And so you go ahead and now fill in that line, right? And we call that vector 2. It's not a bad idea at that point to kind of go like this and say you've gotten rid of that. You have to realize, however, that this vector's point of application is still right there. It's not twisting it out here on the end. It's just that mathematically we add vectors tip to tail. Now you've got the 2. Vector 1 plus vector 2 actually equals that vector here. But now you can go ahead and add vector 3. Once again, you're going to take and put the triangles next to each other, the hypotenuse, and you can start doing your slides here. So you're trying to transfer parallel. If you can come upon a set of parallel rules, that's how it's done in navigation. So you now have that next direction here. You go ahead and actually, once again, now you're going to transcribe the distance from here to here. You go ahead then and graph again along that length. And so you have, in fact, vector 3. This is no longer here. So vector 1 plus vector 2 plus vector 3 equals what becomes, and this is the symbol you'll see, you probably make that heavier or a different color, that becomes a resultant. So you've added vector 1, vector 2, vector 3, tip to tail. These have been concurrent vectors. Later on is when you're dealing with non-concurrent vectors, there's going to be some other manipulation in terms of sliding it around. But if you want to think about this many different ways, you're going to see it mathematically, you're going to see it vector-wise. You've just added up the x's, you've added up the y's, and you've added up the z's. Adding vectors is some way much easier by using lists in a calculator. However, you'll blow signs on that. And if you do vector addition like this, which is the pure way, your chance of blowing a sign or a direction is pretty small. And so we here see just addition of vectors. And so if we knew that these were the external vectors applied to that point, 3 different wires, we would know there would probably be an internal reactive force going the other way. So remember, you're going to be adding more than one vector type on a plane. Use different colored pencils, use labels of scale, and then we'll start talking about both adding vectors, subtracting vectors, which is adding the opposite, multiplying vectors 2 ways, either by cross product or dot product. To take full advantage of the 15 minutes of YouTube fame we have for this, I'm going to show you graphically what it looks like to add 2 vectors, once again using force being brown and now distance being red or green. So I'm going to go here and I'm going to tell you this is basically a wrench, all right, and that is a distance of some value, and it's going to have a force applied to it of some value here. Once again, you see that you've got distance, so that we'll call this a radial vector, and this we'll call a force vector. Now, usually if you're twisting a wrench, you're interested most in the cross product, R cross F, which basically, you remember, it looked like that when you're doing matrix algebra. But how do you go about getting the calculation? By using vectors of R cross F. It is the cross product. And once again, using these tools, I'm going to push this thing off to the side here. You just, once again, now slide and make a parallelogram. Now that you can see, we want to shift our vectors here. We're going to slide off to here. We're going to make some sort of parallelogram through here, right? And in effect, what we're looking at in terms of a value, you could actually go ahead and slide the other one as well. Right? You're going to slide that one up. And we can know that what we do calculation-wise to know the direction of our cross product is we put our fingers out along the radial vector and turn in the second vector the force, and we know that this is a positive torque, and its value is the area right there. And what direction? As we start talking about torque, it's going to be out of the board, because R cross F, it's the same mathematics as the normal calculation. R cross F is always going to be coming out of the plane of the 2 vectors. That also you will realize is going to be equal to, the magnitude is the magnitude of R, so the length of R times the length of F times the sine of the angle between them. So that is the deflection angle between them. And you're going to see there's going to be a lot of other calculations, but at fundamental it is the area of the parallelogram. So that is how you multiply and get a cross product in a plane, and also how you add vectors. So we've seen now how to add vectors, tip to tail, concurrent vectors, how to multiply using a cross product, and the last process then I'll just show you very quickly is, and hopefully not run out of YouTube fame, is distance times force. So it's this distance times this distance times this distance, the projected distance. Very often what you're going to do is you're going to slide that over here. So one has units of foot-pounds of torque, that would be the area one, and the other one has foot-pounds of work, that's the one that does not have an area. Work does not have direction. All right, we're going to post this out. We'll leave those out, see how people think of them. We'll look at them doing it in graphics, doing it in CAD, doing it in calculator, and doing it in 3D. And what you have to realize, it's tough to do this kind of paperwork in 3D, but 3D is where it's at.